Hi, in this screencast, we're going to show you how to do a combustion analysis of a hydrocarbon or of other substances. This is screencast 9.8. The key to understanding combustion analysis is to recognize that every carbon goes to make carbon dioxide and every two hydrogens in your starting material go to make water. Here's our problem. Combustion analysis of 2.4 grams of toluene yields some carbon dioxide and some water in those amounts given. Let's come up with a simple formula for toluene. Start with what you're given. We started with a little over 8 grams of carbon dioxide. We figure out how many moles that is, since 44 grams is a mole. And then we recognize that every mole of carbon dioxide had to begin with a mole of carbon in our starting material. Or another way of saying it is that a mole of carbon dioxide contains 1 mole of carbon. We must have started with 0.1823 moles of carbon. Do the same for water. 1.877 grams of water is a little less than, well, it's a little more than 1/10 of a mole of water. And anytime you have a mole of water, it contains 2 moles of hydrogen. That was present in our starting material. So we have that many moles of hydrogen. If you calculate it through, you'll see all 2.4 grams are accounted for. And that's your formula right there. If you take the big number divided by the little number, you can get a whole number ratio there, at least for the small one. And it's not till you multiply hydrogen by 7 that you see that your lowest whole number formula is C7H8. And that's correct for toluene, shown there. In the second problem, there's a third element present, carbon, hydrogen, something else. Ethanol, for example, contains carbon, hydrogen, and oxygen. Here's the problem. Isopentyl acetate is composed of carbon, hydrogen, and oxygen. It smells like bananas. Combustion analysis yields that much water and that much carbon dioxide. What's the simplest formula for it? Well, in this problem, once you do the analysis, you'll see that carbon and hydrogen doesn't account for everything. See here it all did? In this case, we're going to see what's missing, and that must be from oxygen, and that'll be the amount of our third element in our starting material. Okay, so we have some carbon dioxide, we figure out how many moles it is, and we recognize that each mole of carbon dioxide contains 1 mole of carbon in our starting material, and we find that we have about 1/10 of a mole of carbon. Do the same thing for the water. 18 grams of water is a mole of water. Notice that things cancel nicely there, and every time we have a mole of water, it contains 2 moles of hydrogen that had to come from our starting material. And we have 0.188 moles of hydrogen. It looks like twice as much. But the funny thing is that if you run that through, you do not get your full amount. Where is it? 1.75 grams. You only get about 1.3 grams. There it is. In other words, 0.094 moles of carbon is much less than. You multiply that by 12, and this is about equal to 1 gram, since 1.18 grams, since 1 gram a mole. 1 gram of hydrogen is a mole of hydrogen, and when you add them all up, something's missing. That's how much missing. It must come from oxygen. And 16 grams of oxygen is a mole of oxygen, so there's our missing third element. We have 0.0269 moles of that. So we have a ratio right there. C, 0.0941, H, 0.1881, oxygen, 0.02694. Divide them all by the biggest one to make the smallest one equal to 1, and you have a ratio of 3.5 to 7 to 1. I think you can see here that you need to double everything in order to get a final formula of C7H14O2. And if you look up the structure of isopentyl acetate, you'll see that in fact it does have that many carbons, that many hydrogens, and that many oxygens. This is combustion analysis, screencast 9.8.